Hello, everybody, and welcome to another TopoDOT webinar series for extracting value from MLS data. I'm going to go ahead and help you guys navigate the updates associated with the pavement analysis tools. And if you want to get your hands on these today after this presentation, make sure you have the latest full version for the 2021.1. That I believe happened in September or early September. And if you haven't seen our latest release update, I also recommend viewing the February and early September webinars for this year. So your speaker today is me, Mike Cook. I'm the Senior Applications Engineer over at TopoDOT. I've been with the team for a number of years now, working with the support and development teams to help ensure product quality, delivery, and usability. And I'm not alone. We have a dedicated team to essentially help support the TopoDOT community. For those of you who don't know us, here we are in full cartoon mode. This way, I guess we will never age in this mode. And yes, we're a software development company behind the TopoDOT software, but we also provide training, support, and consulting services. On the call, I have Jennifer, and she's going to be our business developer, so she's no stranger to the community. And also, we should have Mauricio Turnius, our head developer, who's going to be responsible for making pavement assessment a reality for us. All right, so just a first quick look at our agenda. I'm going to give a brief introduction, and we're going to get into, what's the goal of this. We're going to get into some standardization and what that looks like, and the terminology associated with it. What type of distress information can we pull out? What's our approach to the problem, and then what does the workflow actually look like? What are you going to get out of this for results or reporting purposes? And we're going to look at two additional examples as well when it comes to pavement assessment and the like. And for those of you who are unfamiliar with the TopoDOT product itself, I'll just kind of give a brief summary here. So TopoDOT is a high-performance software application for the Bentley environment, the Bentley microstation environment, for high-quality topographies, 3D models, and assets, all from point cloud data and imagery. And this is going to be giving you CAD deliverables to feed those downstream operations across multiple disciplines. But our focus today will revolve around pavement assessment. Okay. And up first is I wanted to kind of explain why we're here, and the goal is to essentially provide a viable solution for the management of pavement networks utilizing mobile LiDAR, TopoDOT, and Paver. So in other words, the goal is to essentially expand the mobile LiDAR into the pavement management segments. And in order to do this, we need to follow three major steps. Okay, we're going to be collecting the data, we're going to essentially analyze it, and then we're going to feed that into the existing management platforms. And when it comes to collecting the data, we're going to be using mobile LiDAR, and we'll discuss in more detail on why MLS data is going to be suitable for this application. Once the data is collected, the raw data needs to be processed and then additionally analyzed in order to pull the intelligent information out, okay, and in an organized fashion. So for this step for the analysis, we're going to be using TopoDOT. We then export the intelligent information from TopoDOT into a pavement management program, such as Paver, where we'll be able to consolidate and make sense of the data at a higher level. So the deliverable looks something like this. Okay. So after applying those 3 steps, what we have here is a final report from Paver, which includes the analysis conducted in TopoDOT. And the ultimate goal is to provide a higher level view of the pavement network. So, you and your client can essentially accurately predict roadway life expectancies, effectively apply funds where and when they are needed, avoid costly repairs with a variety of preservation strategies. Okay. And a little bit of background on this. This project was completed by TWM Engineering. And I used mobile LiDAR and TopoDOT to feed this downstream management platform. It's city of Trenton, Illinois. It's about 18 center lane miles. The total time for both collection, extraction, and reporting is about 60 hours. And if boots on the ground were used or a traditional approach was used instead of the mobile system and TopoDOT, it would have been about 3 to 4 times longer. Not only that, is if you do it traditionally, you can only gather a fraction of the information, less than a quarter of the project when compared to mobile data, because the mobile data is going to allow for 100% of the roadways to be gathered and analyzed. Okay, so what we're seeing here is basically a roadway network that has been indexed or has been categorized into a specific bracket here. So, and we'll get into the definitions of PCI. So we have 0 to 40, that's the worst, and then you have 100. So this is just a quick glance at, what is the condition of your network and why is this beneficial? So essentially, the market wants to manage and sustain their pavement networks in a practical and budget-friendly manner, ultimately providing an opportunity for the geospatial community here. So for example, the more you know about the road network status at this level, the more information the decision-making process is going to have. So what we see here is a typical asset decay curve showing the condition of the road over time, as well as the costs associated with rehabilitation of said roadway. And we can see that if roadway networks are monitored regularly, we'd have a better idea on their outlooks. And the idea is to avoid major rehabilitation, which can be, tenfold in costs when compared to earlier preventative maintenance. So how do we get to a final deliverable that we saw earlier? This is just kind of an opener. And now's a good time to launch some poll questions. Thank you for answering those. It always helps out. So let's cover a few items first, and we'll work our way down into the deliverable. So for pavement assessment to be quantified, we must have a standard way of measuring it. And this standard is going to be the PCI, or Pavement Condition Index. The little bit of history on it. It was originally developed, the standard was developed by US ACE for airfield pavement ratings. And then it was later standardized for roadways by the ASTM community. And that's going to be in the form of the document 6433. So that's the document that we're going to be following and utilizing to assess these roadways. And traditional methods of collection were either done by hand or with primitive forms of equipment. In the right image, we can see an individual looking to measure a depth with a straight edge or a ruler. And they're just kind of walking the field, making notes and kind of subjectively, placing a condition on these roadways. So as time went on, the technology improved and measurement systems became more sophisticated. And one of those systems that eventually became viable for this application was mobile LiDAR. So what is PCI? We said it earlier, pavement condition index. It's going to be a scale of 0 to 100. So this is the value assigned to the roadway sections, with 100 being, a perfectly healthy road and 0 being, the worst case scenario. So that's the gradient it's going to get. And the pavement distress itself, these are the visible deformations of the pavement. So the mobile data captures these deformations and then later to be extracted and categorized into distress types and severities. The sample unit or pavement sample unit, these are going to be the smaller subunits of roadway sections, and they're typically about 2,500 square feet in that ballpark. And then pavement section, these are the sections that make up the roadway network itself. So you have the entire network, but then you have these smaller sections. And typically they start and stop at any major intersections. So you might have like a main corridor road stretching a mile, and then you have kind of distribution roads kind of branching off of that. Even a block, like a roadway block, could be a section. So there's a variety of lengths. That's how it's organized, at least. And then the two main technologies that have emerged for this application are going to be the profilers or the pavement scanning vehicles. That's going to be on the left, and the geospatial vehicles or the mobile mappers on the right. And I'd like to point out a quick comparison between these two technologies. There has been, the pavement scanning vehicles out there for quite some time now. Let's call these our profilers. And they're designed to collect every pavement condition you can imagine at a high resolution. They've got, multiple short range profile scanners and a handful of cameras to match in order to basically collect very specific information on the pavement surface. The entire vehicle itself and all of its equipment are basically integrated into one unit. At the same time, we have a geospatial system, which also collects surface data, but traditionally has been reserved for GIS and topographic applications. And this is probably due to the initial densities and accuracies years ago, but over time, the technology has improved so much that it's now capable of collecting the roadway surface in great detail. And that's going to be key there, because that detail is going to provide the required densities and accuracies needed for this assessment, this pavement assessment. And for the mobile system, the mobile LiDAR, the equipment is bundled into a compact unit that can be shipped and attached to any vehicle. So that's kind of a key difference there. So as data got better, the MLS data sets were in a position to collect similar data at a fraction of the cost. Now we're not really looking to displace the profilers out there because they do have a specific purpose and need. For example, they can get like partial measurements like texture of the road. That's something that we're not going to be able to get from a mobile system. However, there's plenty of other measurements that we can get via the MLS data set. And what we were mentioning earlier about just getting a base map of your roadway network, that is going to be possible with the MLS data sets. Okay, if you're looking to lay out all the crack information, get crack depth, do a further investigation on a beat up road, that's probably where the profiler will kick in, or be a traditional approach where they can measure that information. And since MLS data sets are typically used for beyond the lane lines, such as curbs, ramps, assets, distribution lines, and other overhead structures, we think this is going to give our clients that added advantage because they're extracting much more than just the pavement. So you have a very adaptable and capable remote sensing platform now overlapping into these applications. With that said, let's do a quick kind of summary comparison between mobile LiDAR and profilers. So usually the operational cost for smaller projects is a little bit higher for the profilers, where the mobile is going to be at a lower cost. As I mentioned this earlier, but coverage, for the profilers, you're limited to one lane, per pass. The mobile systems, you're going to get multiple lanes and the surrounding right-of-way per one pass. Okay, the applications here for the profiler are going to be limited to the roadway, roadway assessment categories, where mobile data is going to have, assessment, surveying, mapping, asset inventory, etc. The deployability of these, I mentioned earlier, the profilers, it's the entire vehicle. So you got to get that vehicle to the site. You can't just, ship a compact system like the mobile unit and just mount it on the vehicle that's there. Geospatially, the mobile LiDAR system is going to be performing higher. The accuracies are close, but the profilers are going to be able to go below 300ths of a foot. Mobile LiDAR is, typically above that. Accuracies with no control, so this kind of hits the geospatial part again. The profilers are usually not as accurate. You're seeing 23 to 40 inches of absolute accuracy with no control, where with a mobile you can get it pretty tight with just using the system itself with no control. And then as for a standardized process to get survey accuracy, well, that's established in the mobile LiDAR industry, and it's very repeatable. Not so much for the profilers. Okay, profilers don't really have a system or a well-known strategy for georeferencing these things at survey accuracy. Densities, obviously a profiler wins in this one. Learning curve, well, these systems, the profilers are usually pretty steep, and for the mobile side, we're going to be a little bit more user-friendly. Even in operation, it's going to be user-friendly. I've been told many times that they can kind of just set together a checklist, and anybody can kind of run these systems. And then the data formats, profilers are going to be proprietary. They're going to be closed, where we try to stick with a universal, common, open format that really everybody can kind of really utilize the data. All right, so I probably have to speed up. Already eaten away 30 minutes, so I'll try and stay on track here. So what does the data look like in TopoDOT after it's collected? What we're looking at here is mobile LiDAR from a typical leading manufacturer, which gives us a lot of detail, enough to get the job done for this PCI application. And keep in mind, this is from one single pass and also a single scanner head. So it's pretty impressive. And the left image is a top-down perspective, viewing only the point cloud data itself. You can actually see that the densities are high enough to almost form a black and white image of the roadway. The right image is going to be the camera, and that's actually our camera perspective, which we're viewing both the point cloud and the calibrated image because it's overlaid. And just a quick curve profile, you can see how tight that data, the relative accuracies here, are great for doing this type of assessment. But if we want more data and better coverage, we opt for a dual head scanner. That's going to give you that distinct crosshatch pattern seen in the left image. And the reason for that is it's just going to help you reduce shadowing, or it's going to reduce the footprint of the shadow. Notice the semi-truck on the right image. While one scanner was blocked, the other one filled in. Think of it as kind of two spray cans in sync at different angles to get, the coverage that you need if one of them is being blocked. So what this means is that this setup is going to provide better coverage for the neighboring lanes, and we'll see where that comes into play later on. And a quick word on data requirements. We recommend a single pass for the best results and to ultimately save time. As good as these systems are, there's going to be minor differences between two different passes, especially if we're not using control. And we don't want these differences to be mistaken for a false distress item. And although they can be aligned, you can align two different passes, it's just going to require more time. Therefore, we recommend a single pass per analysis. Okay, we'll see how many lanes we could process at once. So what will a single pass get you? It should be good for at least 3 lanes total, possibly more in some cases. Those lanes are going to include the driven lane and both neighboring or adjacent lanes on either side. Okay, seen here in the image as green arrows, those are going to be our driven lane and adjacent lanes. And depending on the system that you use to collect this, and also the speed of the system, the additional lanes out at the edge there could also be captured too. That's in yellow. But in some cases, it's just a matter of strategy to capture as much as possible within one pass. So here we can see the drive lane has been shifted over into the shared lane to get the entire roadway here. So if that's possible, great. But for larger corridors, you're going to have to collect more passes, and you'll just be keeping them separate during the analysis phase. For example, highways have barriers, for example, so a single pass per bound might be sufficient. And then just kind of a quick summary of the best practices for the collection. So yeah, we recommend 2 scanner heads on the vehicle. We recommend 1 trajectory per analysis. Usually you'll get 3 lanes out of that at least. And how many lanes can you do the analysis? How many lanes can you handle for the analysis? And that's ultimately going to be 3, like we saw previously in the image. For cameras, it's best to have the dedicated cameras. You can try and use the ladybugs, but we're thinking that the higher resolution ones, 5 megapixels and plus, are going to be optimal for visualizing these cracks. Because remember, we need the images to actually visualize the cracks. The LiDAR data isn't going to be telling us the crack information. And then the orientation of those cameras is best to have them pointing backwards and to the horizon, kind of like what we see here. No obstructions from the vehicle. We want to make sure that we capture these at the correct interval so that we have enough images to gather that lane line information. You can also do kind of like a backwards right and left situation. So if you're looking to get a bigger field of view, you can have 2 cameras with a little bit of overlap to help with that. So we're going to be interacting with the images when it comes to the user identified distresses. And what surface types is this going to work for? It's going to work for roadways and parking lots that are asphalt only. The concrete roadways, that's going to be a separate process, and that won't be possible with our tooling for today. So as long as it's asphalt and it's roadways or parking lots, you should be okay using our tools. And a note on noise or fuzziness of the data. I got an example on the right here. We definitely want to be working with systems that are capable of not exceeding 300ths. And we should get that in one pass. If you start to do multiple passes, then it might introduce a little bit of fuzziness to it, but we definitely don't want to work with the fuzzier data sets because the distress information is going to get lost in it. As for densities, we're going to recommend 100 points per square foot, and we don't want our scan lines to be separated more than 2/10 from each other. And the idea is we just want to make sure that we're getting enough density to cover the entire distress item so that we can really get a good idea of what it is. I have seen distress, pulled out from, 50 points per square foot, but it just depends. We just recommend 100. So what is possible? What is possible to basically pull out from these mobile data sets? And we've broken them up into two categories. We have the automatic distress types, and we'll see later on the user identified ones. These are going to be all the low frequency objects that are large enough to be collected within, the point cloud alone. So we can actually see these in the point cloud itself, and we'll be measuring off the point cloud to find these guys. So we got bumps, potholes, rutting, all the large items there. For the smaller items or the more difficult ones to automate, that's going to be user identified, and we're talking cracking, bleeding, patching, things like that are not going to be as easily measured in the LiDAR data. So for cracks, we'll definitely need to rely on the imagery, which we're going to see later on. And that's essentially because the cracking is just too small to be detected with the LiDAR data alone. So it's ultimately key to have user-friendly tooling here to allow for optimal interaction with the point cloud and the imagery when you're looking for these things. So we're going to apply automation where we can, and then we're going to finalize it with these necessary user-identified tools. And it's important to note, too, that both the automatic and the user-identified distress items can be done in parallel. This is going to allow teams to work at the same time on two different categories of distress. Okay, all this work is going to eventually then be consolidated for the end results. So you don't have to wait for one distress type to do the other. So how do we accomplish this with mobile data? We're going to break this down into a few major components. How we sample and break the lane lines down according to ASTM standards, how we flag or identify the potential distresses, how we are finalizing the distress items through automatic and user-defined procedures, and ultimately generating reports. So we're going to break it down into those components there. So to start, we need some type of boundary information or boundary lines that provide the best approximation of the ideal lane line. And since paint stripe lines are least traveled, they provide an excellent reference for setting up an ideal lane surface. And keep in mind, paint stripe lines are going to be the easiest to extract out of the topography tools, so that's always a bonus. And what we're going to do is we're going to break these segments. So we're going to take the lane lines and we're going to break them up into segments, and they're going to be approximately 10 by 10 foot blocks. So in this image, we can actually see one of those blocks. The left and right wheel paths are going to be colorized here in green and yellow. Okay, so what we're doing too is we're going to break that block up down the center, and we're going to be left with two planes, per block. So now that we've set up our ideal reference planes, we can now determine what point cloud data is going above and below these ideal planes. And the deviations of these distresses or deformations will then be compared to the thresholds defined within the ASTM standards. And what we'll be able to do from that is we can then produce a colorization of how this data behaves outside of these planes. So we can kind of see it colorized here of the data coming above and below those planes. Now we need to take a look at how we categorize these distress objects. So since we can isolate the data outside of our planes, which we can kind of see here, we can now categorize these objects based on, the shape, the size, the direction, the depth of the clusters that we're isolating. Now here we could see thousands of classified distress points, like actual point cloud points. And what we're left with after the analysis is a simple shape element per cluster or object. This can be seen in top view via the outline objects. This is going to keep file sizes down, and ultimately is going to become more compatible with other platforms. For example, you could take these shapes and send them directly to Google Earth. We took this approach of outlining because delivering the point cloud is sometimes just too much data, or is just not compatible with downstream operations. And then the exports can be in a variety of formats, the most common being Excel and Paver software exports. You can also take these graphics and convert them into a shapefile for Esri. You can make a simple KML for Google Earth. You can also export these graphics into a variety of other CAD formats. If you want to go to AutoCAD, you could take this information. And all the reporting that we do is going to be based off of the ASTM 6433 standards. And each distress is going to have its own specific threshold and weighted value that we basically combine and consolidate into the final report. All right, so now it's time to look into the workflow and the tooling involved. So first we're going to need our paint stripe lines for the boundary information. So let's go ahead and take a look at what that looks like. So we're using the extraction by intensity tool to pull out these paint stripe lines. And if you're not familiar with this tool, basically it's you're giving it a direction. It's going to be sampling at a specific interval, and it's centering itself and then draping itself to the data. And what the user has done is isolated the intensity ranges outside of the stripes so that we're kind of not even seeing that. We're seeing what the tool's seeing in these views. And then for like edge of pavement or something like that, we do want to have, if we have a lane line without an edge line or a fog line, we want to include an edge of pavement line, which you could do with like a tracing and draping routine or using the break line tool. Now that we have the boundary lines, we can then run the auto distress tool. So let's see this in action on this is about 1,500 foot stretch of road here. So you'll grab your lane lines. And with those, so this is a section of the road. So we grab those lines, we hit process. Right now we just have the default set to ASTM standards. And what it's going to do is it's going to colorize the data. So you can do RGB, you could do classification based off the ASTM thresholds. And it's also going to give us that graphical work that we saw earlier. Okay, there's other plotting items such as like the blocks, and you could do the center line, but ultimately what we're after is that distress information and the blocks. Now we're going to take a quick look at the user-defined or user-identified distress, such as cracking. This can be done in top view or within an image view. Remember, we also have that high resolution imagery that's overlaid onto the point cloud. And what you'll be allowed to do is draw shapes and lines with the corresponding metadata. So what you do is you pick the distress type and the severity before placing these shapes and lines. And note this could be done with a team working in parallel to the other processes seen earlier. There's no need to wait for one process to be completed before the other, because all this distress information is going to eventually be consolidated into the final report. And alternatively, we can, instead of using a calibrated image, you can also consider using an ortho photo, a high-res one, that can be simply rastered in for quick work in top view. So what's happening is, as the user is clicking in the image, it's basically sampling the data behind it, and it's placing it, correctly or horizontally correctly on the data itself. So what you're going to have is you're going to have a mix of your automatic distresses, and then you're going to have a mix of your user-defined distresses. Here's kind of an example of if you're looking to just trace something out, you can technically do that. And then we got the sample size listed there too, how much data you want to grab as you're clicking into the data. You don't have to hold control, you just hit define region and you place it in there. Now you could do small bits, you could do large bits. I've seen people do the entire lanes. You just kind of add that metadata, that shape, to the entire lane or to the whole section of road, and you just specify, yes, this whole roadway has block cracking at medium severity. So that's kind of the idea. You just lay these things down to be included in that final report. All right, so now that we have all of the distress identified, we're going to export them. So this export is going to handle both the large distress items and the cracking. So what you'll do is you'll basically select all of your blocking for that section of road. You're going to create these sub-unit or sample unit blocks. That's the 2,500 square feet that we mentioned earlier. And they're going to each get their own PCI value, okay? Once you're done doing that, you'll then grab everything together to kick out a final report for that section. So it's going to take all those sample units, list them out into Excel form, where you'll have quantities and volumes and the PCI value for each one of those, and then you'll have your overall PCI value for the entire segment. And another advantage of the mobile data is you could advance through the imagery just like this, and it's almost if you're just kind of like driving through the project. So you can easily navigate through these road networks with the imagery like that. All right, so a quick summary on this for the tooling itself. So this was completely rewritten from the older legacy version. And again, we're using this for calculating PCI values for the roadway surfaces itself. And we're ultimately feeding that pavement management platform, such as Paver. The bigger improvements that we made for this tool is just a better user interface and interaction with the imagery. We wanted to also make sure that the teams can work in parallel, so you can get the cracking information and you can go after the larger distress items automatically with two different teams and then bring that information back together. We added support for making edits and updates, So in the event that you were going through and you wanted to make a small edit or add something in, you can now do that without having to start over. We ultimately added an export for Paver. We're looking to add exports for other platforms too, but Paver seems to be a pretty common one right now. And previously we had icons of representing the distress items and the severity. Well, now we have those outlines, which are going to be a huge bonus there. So we at least know the footprint now. And just a quick testimonial from our clients. So Jeff Clay from TWM, he likes the fact that the subjectiveness has been removed and is safer for his team using this approach. Joe Fader from REY Engineers likes the Paver export itself, and he loves the fact that those distress outlines are actually geo-referenced. So that's something you could take to a different platform, such as Google Earth or Esri. And some additional information or additional results that you could go after is, we're calling it an optimized surface mesh, but what we're really doing is we're mixing the road extraction tool where it's getting the key points along the profiles, and we're mixing those with the points generated from the pavement assessment routines. So not only are we kind of bundling the point cloud data and producing outlines, but we're actually producing points within those potholes, within those ruts. So with that detailed information in CAD point form, you're mixing that with some other CAD points to produce kind of an optimized representation of that surface. So you take those points, you can make a mesh out of them, whether it's in a MicroStation or somewhere else. Rather than having a point every inch, you've kind of reduced it down to kind of focused densities. So instead of having 1 million points, you might reduce it down to a couple of thousand. Another good one is roadway geometry. Keep in mind that all you'd have to do really here is, you could work straight off the point cloud data, but in this case, if you have the paint stripe line extracted already and maybe the barrier information, well, you can just quickly dart through and generate, cross-sectional information, grade, what's the width of these lane lines. Common application for this would maybe be like post-construction to, verify cross slopes, for example. And again, control technically isn't needed in this case. We're just running it straight off the mobile data after it's been collected without control, because these are all basically relative measurements. So again, you're going to get a report to give you width, cross slope, grade, and things like that. Great little tool. This one's going to be I believe it's the slope from lines within the analysis tools. And then additional features we want to kind of throw out there, the TopoShare platform. So, how do the benefits of LiDAR span across operations? We've, added a web sharing portal for communicating with, internal teams, customers, and partners. And we're calling it TopoShare. Some of you may be familiar with this already. If not, definitely go ahead and contact us if you'd be interested. But the foundation of this process is provided via an easy-to-use front-end web portal, which is going to put the data at everyone's fingertips via just a simple URL link. And this means that multiple departments can collaborate on the same projects without being a data expert. You don't have to be able to run CAD or anything like that. You just click a link and there's your project. You can also simply just request what you need and where you need it. So you can put in markups. Should probably play this. So you're going to get line work. You're going to get aerial information overlaid. Here's actually an example of a pavement assessment project, the one that I was just kind of working on. So we've added that line work in there. We've added some of the metadata in there with those little information bubbles. Also, too, you can navigate and view imagery in here. We'll see that in the lower left-hand corner shortly. But you also have your point cloud overlay in here. This is just a raster representation of the point cloud. There's the actual distress information isolated in point cloud form. So maybe instead of doing the outlines, you can give them a raster of the point cloud information like this. And here's those images coming into play. So you can navigate and view the images from the system itself. You can also take measurements within these, such as height and width. And this is possible because the actual 3D spatial information from the LiDAR has been embedded into the photo. So we can kind of see that there as they go through some of the channels. And this web portal is going to essentially allow all parties involved, to review the projects at hand, send markups directly to the CAD teams via KML, and ultimately to receive quicker turnarounds and or better, geospatial information as they go through the life cycle of the project. All right, so why is all this important? Well, we're trying to expand the market here of the mobile LiDAR with this newer application for road assessment. We can always work remotely with this type of data. The LiDAR technology from the mobile units are going to have a wide variety of applications, not just the pavement assessment. All the extracted work is going to be geolocated. We're going to see improvements to productivity, lower cost, and just repeat trips to the field, especially when compared to traditional methods. And the extraction software is on a common Bentley MicroStation platform. So it's very available for a lot of people. So we were talking about proprietary formats and proprietary softwares from these profiler systems out there, but we tried to bring that down. We try to bring our formats to a universal format so that everybody can kind of use it in an easy to use CAD platform. And then moving forward, so adding to the pavement assessment, we're probably going to be looking into Street Saver or possibly Pazer. It's similar to Paver, but it's just another pavement management program. I'd like to see some improvements for the user identified distress types. So we might add the support for like placing shapes and then assigning metadata, or using the lane lines themselves to like flood. You could do like a flood style shape creation within a lane line. And then we're also going to look into continuing development for the IRI and straight edge tools and any other pavement assessment tools, really. All right, so let's go ahead and open this up for questions. We got a few minutes left. We'll go ahead and leave you with our contact information as well. And I'd like to thank you for your time.
Great job, Mike. Well, we did have a couple of questions. A few people asked whether these could be used, or these tools can be used with other scanners, so like static scanner or UAV. And it can be, as long as the data matches the requirements that Michael was talking about. basically the coverage, the data noise level, the density. So if you can achieve that type of quality with your point cloud, then you can apply it into any other system, not just mobile laser scanning. One other question here is that if can these be used in other standard that is not the ASTM, or in other types of roads that are not necessarily road, like a runway or something like that? And it definitely can. You can plug in your own values, your own measurements for distress. The ASTM standard is a set on the tool, but it's not necessarily the only option. There is a lot more information on the training material associated with this tool, which you can find on the university, on the analysis videos, or at the wiki page for this tool. So there you can customize the tool to your needs. But I think for now, that's pretty much it. Like I said, if you have any questions about the actual understanding the tool, or the process, the workflow, I know this was a little bit brief and over the top, but it's really very simple. There are more training videos on the university, and you can also contact us directly if you have any particular questions about your project. All right, well, that's it. Thank you very much for attending another webinar, and please fill out the exit survey and let us know what you want to see next, or what you want to learn more about in for our next webinar. And we thank you very much, and have a good rest of your day.